Hello everyone, and welcome to the Tuesday press briefing at the 49th Division of Planetary Sciences meeting. I'm Shantanu Naidu, I'm the DPS press officer, and with us is Rick Feinberg, who is the AAS press officer. Today we have three very interesting topics at the press conference. First, we'll hear from Vishnu Reddy from University of Arizona about the ground-based characterization of Earth Quasi-Satellite 2016 HO3. Next, we'll have Alan Harris from MoreData presenting the population of NearEarth Asteroids revisited. And after that, we'll have Juliet Becker from University of Michigan talking about the dynamical stability of outer solar system objects in the presence of Planet 9. So first, we'll have the speakers speak in order, and then we'll take the questions later. Before we begin, may I remind you to please either turn your cell phones off or put them on silent. And I'll hand it over to Vishnu Reddy.
Okay, thank you, Shantanu. So we did ground-based characterization of a quasi-satellite of the Earth. It's called 2016 HO3. This object was discovered in 2016 by the Pan-STARRS telescopes in Hawaii. It's an Apollo-type asteroid with a size between 40 and 100 meters across. It orbits the sun, but it also circles the Earth as a quasi-satellite. So I'll switch ahead and I'll show you a quick movie. Oops. I guess the movie's not playing. It's going? Okay. So here what you see is that the sun and Earth's position are held fixed, and the red circle you see is the object's orbit around the sun, and the yellow circles that you see are what an observer on the Earth would see as this object goes around the sun. So there are 5 known quasi-satellites. Most of them are short-lived in the Earth system. 2016 HO3 is a stable one, and it's going to remain around the Earth for a few centuries. So it provides us with an opportunity to explore this object either robotically or with human exploration, if that's still an option. And it never strays beyond like 100 lunar distances. The closest it gets is about 38 lunar distances, and this happens about every April of the year. So middle of April, it comes close to the Earth. So the rationale for us to study this object was that it could be derived from an unknown Trojan asteroid population. So we also wanted to find out if this was a real object or a man-made object. So our goal was to find out what this object was made of when we started this study. We also wanted to find out how fast it spins so it can tell something about its man-made or natural state. Given its, despite its proximity to the Earth, which is only 38 lunar distances, this object is quite small and faint to observe. So traditionally, we use the telescope, which is the NASA IRTF, to characterize asteroids. It's one of the best telescopes in the world to do that. But in this case, it was too faint for that telescope, so we had to use the large binocular telescope that is run by the University of Arizona. And this telescope has an instrument that is capable of characterizing objects that are really faint. So in this case, 2016 HO3. And we observed this during the last close approach, which was this year in April. And we also got data from the Discovery Channel telescope run by the Lowell Observatory in Flagstaff, Arizona. So quickly to show you how fast this thing spins. So what you see here is a light curve of the asteroid. It's nothing but as the asteroid spins, the surface area that is reflecting sunlight changes. And so you see the sinusoidal pattern. Whenever the broadside is shown, you see an increase in light, and whenever the narrow part is shown, you decrease in light. So the asteroid rotates once every 28 minutes, just like how Earth rotates once every 23 hours and 56 minutes. So the other thing we did was find out what the colors of this asteroid was. The colors tell us something about its composition, what type it could be. In this plot, what you see are the red dots are like carbonaceous, which are darker objects, C-type asteroids. The green ones are X-types, where we don't have any brightness information. And then the blue dots are S-type objects, which are mostly silicate objects. So this clearly falls mostly towards the silicate side of things than the carbonaceous side of things. The final plot I want to show is a spectral plot. What you see is the reflected light from this asteroid in the visible wavelength range So it's going from about 0.4 to about 0.9 microns. The red line is the spectrum of this asteroid, and it's very similar to a rare type of asteroids called the Ltype asteroids. So what are these Ltype asteroids? These Ltype asteroids are something like a silicate asteroid, but without the absorption bands that you would usually see with a silicate asteroid. And they typically have a relatively low albedo of about 15%. Typical S-type asteroids are somewhere between 25 and 30%. So it reflects, pretty low light. So just want to summarize what we found so far. It appears that this object is natural, similar to an L-type asteroid rather than a man-made object. It rotates once every 28 minutes. And we use the albedo from an L-type asteroid to constrain its size, and it's right now about 50 meters across. So we have a 50-meter object that is possibly of some exotic composition, relatively close to the Earth, that's available for future robotic exploration. And with that, I will ask Al to come and talk about his work.
Let's see what we do here. And this is the reset button I need. Okay, wow. It actually got loaded again. There was some problem with the loading. Well, we hope it works. Okay, I've been doing population studies in support of NASA's NearEarth Asteroid survey work for I've been doing the population studies for 20 years or so, mainly to assess the progress of these surveys, but also scientifically to know how many of those things are out there, and in terms of impact hazard, what's our chances of one with our name on it. So what I did this year and what I'm reporting here is, first of all, I have updated the population using the last 2 years of survey data. And I do my estimation by looking at what fraction are redetected, already known objects versus the freshly discovered objects. And if all asteroids are equally easy to discover, that number would just be the completion. But in fact, it's not, because some of them hide from you and some are harder to find. So the completion actually lags the redetection ratio. What I did in this last year and a half or so is I discovered that I'd been making what I thought was a trivial kind of round-off thing. I hadn't paid attention to this minor planet center that tabulates all these objects. It tends to round their H magnitudes by 1/10 of a magnitude. And so my bins that I have to sort things in, when I bin things by absolute magnitude 17.5 to 18, I was really actually binning binning in what amounted to 17.55 to 18.05, and that 500ths of a magnitude sounds like nothing. In a certain sense it isn't, but when you get very, very close to completion, it starts to really matter. Now, my last estimate that I just made is 921, where I have corrected those bins. The one I made just before that was 990, and since we know how many we've already discovered, which is 880 something, the difference between 921 and 990 is a factor of 3 or so in terms of the number that are still out there that we haven't discovered at the big size range. Now, when we go down to the small size range, it makes no real difference whatsoever. We really can't estimate the population at 10%. And so that round off error, it makes no effect whatsoever in the smaller size range. Excuse me for, I put a lot of words on these slides, and they will be available to the press if you just download the press stuff. I'm not following the text too much, and it's going to get even worse in terms of this. After I made this correction, my estimate dropped from 990 to 921, and the correction came to my attention when I was refereeing a paper by Tricarico, which is now out in Icarus, and I think the reference is there. And he got 900. And that was a difference in 900 versus 990 when you've already discovered 880 of them. is really raises your eyebrows. And so I looked carefully at his paper and discovered that he had made exactly the same mistake as me, but he'd made it in the opposite direction. So he was actually looking at boxes that are shifted 0.05 magnitudes the other way. And I pointed this out to him directly and also in the referee's report. And after he patched up his model and I patched up mine, he came up with 920 and I had 921. So that's way better than the actual accuracy of those numbers. So we have come in a complete agreement. I'm very pleased by that. He used a rather different analytical approach to doing, he didn't use the redetection thing. And so the fact that two different methods, although given the same data set, come up with the same answer is very encouraging. So here's the cumulative population estimate I get, and on the black line in the figure there is Tricarico's estimate, and the red boxes are my estimate. You see they just kind of zigzag back and forth. All the way, I'm afraid that some of those scales you can't read, but the scale at the very bottom in the light green goes from about 3 meters diameter up to 10 kilometers in diameter, so it covers a big range of size, all the way down to objects that hit the Earth every year or so. And the various colored boxes at the upper left are actually bolide estimates, bolide frequency estimates converted to diameters as best we can. And they seem to be just a little high of our population estimates from the surveys, but not bad. They're a factor of 2 or so higher still, and that could just be accounted by we don't know the densities of the objects, we don't know quite the diameter conversion, although I'll come to that next. And so I rate that as actually a pretty decent agreement. Now then, the next thing is what NASA wants to know, and the news media for that matter want to know, is not this arcane H magnitude business, but actual diameter in kilometers or something. NEOWISE, the infrared satellite of the last 5 years or so, has opened up the possibility to make that conversion. They have measured the diameters rather directly with thermal infrared, and knowing those diameters, they can then look at the optical measure of brightness and calculate an albedo or reflectivity. And what you see on the left is a plot of just diameter versus albedo, and you don't see any obvious trends there over two orders of magnitude of size, from 100 meters to 10 kilometers. And so we make the rash assumption that it's constant with size, that is, that albedo distribution is the same over a range of size. And so on the right-hand plot is that albedo distribution as derived from the distribution of the WISE or NEOWISE measures. And we can then take that distribution and try to transform a population with H magnitudes into one with diameters such that it follows that distribution. Now, unfortunately, because of the slope of that size frequency distribution that I showed, there are so many more really small objects than there are big objects that when you look at the distribution at what I call constant diameter, that distribution is distorted when you change that into the magnitude or the albedo distribution at constant magnitude. And so because there's so many more bright ones, the high albedo objects, there's many more of those, and the distribution distorts in favor of the bright objects. And to try to do that transformation, the worst part about it is that varies on the slope varies, or the distribution varies with the slope, and so it's not a constant. Well, we can play a game of Sudoku here to derive this. This is a table that has across horizontally the 9 different albedos that you see in that previous histogram, and vertically is in diameter in kilometers. If you draw a diagonal as drawn in the red there, that turns out to be a set of boxes of the same H magnitude. And so this particular game of Sudoku, the rules are that diagonal, boxes along that diagonal have to sum to the known population that we have determined, the number of objects at a given value of h that we know. And then the trick is to replace in those boxes, instead of the h numbers that are in there, is stick in numbers that represent the number of asteroids that fit that belong in that box, in such a way that horizontally they will match the albedo distribution of those plots that I showed of from the NEOWISE. So we have the distribution of albedos horizontally according to NEOWISE, and the diagonal according to the distributions that I calculate. And you have to fiddle it around until it gives you the best fit, and then once you've done that, then the sum of the boxes horizontally will be equal to the number of objects at a given diameter that you're actually trying to find. Here's an example solution. I won't dwell on that, but it comes out pretty accurately. And so I then, on the plot on the left, is what we call differential distribution. That's the number per box, and each of those symbols is one of the boxes of number of asteroids at a given diameter. And that goes on the top scale. The scale across the top is in diameter. And I've overlain that or adjusted that to give the best matchup with the number as a function of h, absolute magnitude. And you can see if you just slide those horizontally until the two curves match up, it matches very, very well. And so it is actually pretty good to just use a value of h equivalent to a given diameter as a proxy and just do number of h as a function of h and just write a new scale on the bottom, which is what we normally do. On the right, you have the cumulative population, the running sum of the plot on the left, and that's the one I showed the first time, and it's not really very, the diameter one is not very different from the H one. They're really very close. So here's the summary of my points. The first is the new population, 921, which I think is very solid, represents 96% completion down to the H of 17.75. In the small size range, we have pretty good agreement with the bolide frequency rate. And lastly, the conversion to diameter, which is a little squishy because I can invoke different population distribution or albedo distributions and get significantly different answers ranging from about 750 to almost 900 of number larger than 1 kilometer. So that 830 number is a bit squishy. But the good news here is that the 96% completion is really very solid. And so the number of things out there 1 kilometer and larger, even though we don't know that number too accurately, the number remaining to be discovered is in the neighborhood of 30 to 40, some number like that. Okay, I think that takes care of me, and I will push the button here and see what happens.
All right, hello, I'm Juliet Becker from the University of Michigan, and today I'm going to talk about the dynamical stability of objects in the way far out part of the solar system and how Planet 9 might influence their stability. So first, I'm going to introduce exactly what Planet 9 is for those of you who might not have heard of it before, or maybe not in a while. So Konstantin Batygin and Mike Brown in 2016 suggested that there might be a 9th planet, not Pluto, but a different, bigger planet in the solar system. The reason that they thought that this extra planet might be there is that if you look at the orbits of small rocky bodies smaller than Pluto that orbit at an average distance of more than 250 times the distance between the Earth and the Sun, then you can see on this diagram here, the orbits all seem to point in the same direction. And if these orbits were just assembling by random chance, then that would most likely not happen. So Planet 9 could explain the way that these orbits are oriented. Now, in my work, this argument that was first used to propose Planet 9 is the alignment or clustering argument. In my work, we're going to look at a different aspect of Planet 9's effect, which is the dynamical stability of these trans-Neptunian objects, these rocky bodies in the outer solar system. So to look at that, first I'd like to show you a video of one trans-Neptunian object in the solar system. So this is a simulation, a computer simulation of Sedna's orbit. And you'll notice that the orbit looks pretty regular. So in red is Sedna, that's the trans-Neptunian object. Its regular orbit seems closed, but now I'm going to show you a much more interesting object. So this orbit, as before, the yellow and gray right in the center is Neptune's orbit. So all of our known 8 solar system planets fit within that small area. The red is a trans-Neptunian object. And what you'll notice is this one, unlike the previous plot, this different object's orbit is changing over time. The reason for this is that every time it passes so close to Neptune, it gets a kick, which can change its orbit, and what we just saw at the end, which I'll play again, can eventually result in the object being kicked out of the solar system entirely. So there's a few other ways that these trans-Neptunian objects can die. So they can also be hurtled into the sun, or they can collide with another planet in the system. But either way, this is a problem because some of these trans-Neptunian objects, this happens on relatively short timescales. So Planet 9 actually can prevent this from happening. So let's take a look at a new numerical, so this is another computer simulation. Same object as in the previous slide, but now I've added one new thing to the simulation. So this new gray dot that will trace out a gray orbit is a version of Planet 9. So if you watch this plot, then what you see is the object is still getting those little kicks from Neptune. The orbit, the red orbit, is still changing a little bit. And you can see sort of it changing a little bit. What we're going to see really soon is we're going to see a really violent kick from Neptune. But instead of the object being kicked out of the solar system, its orbit changes. So it hops to a new orbit. So Planet 9 actually can dynamically enhance the stability of these trans-Neptunian objects by, instead of having them be kicked out of the system, trapping them in new orbits. So this is a completely separate argument from the clustering argument that was used to propose Planet 9. It appears that if Planet 9 is real, and if it's in the solar system, that it can help these TNOs live longer in the solar system. Now, the original population of objects that fit in this dynamical class is only a few objects, but we ran computer simulations of the 8 known objects at the time to find out which versions of Planet 9 could actually allow these objects to stay in the solar system. So on this plot, on the x-axis, I have the semi-major axis of Planet 9. That's its average distance from the sun. On the y-axis is eccentricity. So eccentricity is at the bottom of the plot, closer to 0. That's a circular orbit. And then as you get higher eccentricities up towards 0.1, that's an extremely elliptical orbit. So the reason that the orbit of the TNO in the movies looked not very circular and more like an ellipse is because it was an eccentric orbit. So in red is the versions of Planet 9's orbits that allowed the process of protecting the TNOs from being kicked out of the solar system to happen. Now, I mentioned that this argument is separate from the clustering and alignment argument, so we also, from our computer simulations, were able to figure out the orbits of Planet 9 that allowed the clustering that was seen by Batygin and Brown to happen. And that's the green region. So the green region causes clustering, the red region causes the TNOs to live longer. The overlap right in the middle are the orbits that are most probable to cause both of those effects. Now, I mentioned that we've done these computer simulations with only 8 objects because there were 8 TNOs that fit into the class at the time that we did this work. But the Dark Energy Survey, TNO working group led by Professor David Gerdes at the University of Michigan, has been working really hard to use the Dark Energy Survey's wonderful data to find new objects that fit in this class. So there are hundreds of objects that we've been working to characterize. I'd like to introduce you to one particularly interesting one. So we've nicknamed it Kazoo. So this is actually the object that I showed you the videos for at the beginning. This is the one where if you don't have Planet 9, it can get kicked out of the solar system pretty quickly. And if you have Planet 9, it can live in the solar system for longer. So this is a really extreme trans-Neptunian object. Its average distance from the sun is 450 times the Earth's distance from the sun. Its eccentricity is 0.92, which is pretty close to that upper limit of 1. And then its inclination is 54 degrees. So if the solar system planets are in a plane, this orbit is tilted 54 degrees relative to the rest of those. So this is a very intriguing object, and hopefully many more objects of this type will be found so we can help inform the Planet 9 hypothesis even further. So what I'll plot here is just a few plots. So these are the angles that were used in the work by Batygin and Brown to predict the existence of Planet 9. We note that Kazoo's angles, both of argument of perihelion, longitude of perihelion, and the longitude of the ascending node, all seem to fall pretty close to the value that they should, as predicted by Batygin and Brown. And if you want to see these plots more later, feel free to talk to me and I'll show them to you. However, we do note that this, although this object is consistent with the Planet 9 hypothesis, it's not necessarily evidence for the Planet 9 hypothesis. So we need to do a lot more work to figure out. Hopefully Planet 9 will be detected directly in either dark energy survey data or by another survey. But for now, without a direct detection, all we can use is these kinds of indirect methods to try to predict Planet 9's orbit even without seeing it. So in summary, the two most important results of this research is first, from the computer simulations of the solar system's history that we've done, we found that certain versions of Planet 9 can actually enhance the stability of objects in the outer solar system. And then secondly, we announced a new exciting TNO, which we nicknamed Kazoo. All right, thank you.
We'll take questions now. Before you ask your question, wait for the microphone and please announce your name and affiliation. Alexandra.
Alex Witzy with Nature. My question is for Juliet Becker. First of all, what does Kazoo mean? And secondly, what's the time frame over which Planet 9 could be in existence to help explain the TNO orbits that you're seeing? I mean, would this persist for millions, billions of years?
So the first, is this working?
Is there a button there? Yeah, there seems to be a button.
No, I think he controls. Yeah.
Okay, thank you. Okay, so for your first question, the name Kazoo, it's actually kind of a lengthy story. The last bit of it is it's the Portuguese word for cashew. So it's a lengthy story that comes from the internal identifier that we used to identify the object, like the numeric identifier. And then the second question was, how long does Planet 9 need to...
Is this stable for billions of years, millions, billions of years?
So Planet 9's orbit, most all of the orbits that we tested would be stable for the lifetime of the solar system. Planet 9 is not really affected by these trans-Neptunian objects because they're so small. The trans-Neptunian objects are very heavily affected by Planet 9.
Kelly first and then Jay.
Juliette, just a quick, Kelly Beatty, Sky and Telescope, just a quick follow-up. Kazoo is the nickname. Does it have a minor planet center identifier? Has it been announced?
Not quite yet. That will be forthcoming soon.
So the cart is kind of before the horse? I mean, how soon, I mean, when might we expect the NPC to release something on that?
Well, we're in the process of writing up the paper, and then we'll submit the observations immediately after that.
Jay Pasterkoff, textbook author. I was just wondering whether you can explain in words or logic just why the stability is caused rather than just a numerical simulation.
Yes. So the idea is that without Neptune, so Neptune has resonances, and objects can fall into resonance with Neptune, and then their stability can be boosted by those resonances. Without a Planet 9, then the gravitational effect of those resonances sort of falls off with higher semi-major axis. But if you place Planet 9 at 600 or 700 AU, it brings its own set of resonances into the situation. So what you're actually getting is you're getting these TNOs living in resonances with the realization of Planet 9 and hopping between those resonances.
Any online questions?
Yes, we do have some online questions. So the first one, and all subsequent ones at the moment, are going to be from freelancer Rick Lovett out in Portland, Oregon. The first is, how big is Kazoo? So that's for Juliet Becker.
So we actually don't know Kazoo's exact diameter. If from its absolute magnitude, we can assume an albedo of 10% and estimate its size to be around 480 kilometers. But we'd have to get more observations to truly determine its size.
Okay, and then Rick Lovett also asks, well, he knows that Mike Brown, for example, is here in the room. And this question is for Juliette officially, but if Mike or if Elizabeth Bailey, who's also in the room, going to be talking about Planet 9 this week, if they want to answer to or contribute, that would be great. He wants to know what these discoveries or these ideas imply for the current ongoing search for Planet 9. Does it suggest they should be looking in any particular place, maybe that they haven't been looking, or that they should adopt a different strategy, something along those lines?
Well, I can speak for the dark energy survey data. We don't really get to choose where we look because dark energy survey data surveys an eighth of the sky for 5 years. So we'll just get the data that they give us. So the team led by Professor Gerdes is working hard to try and see if we can recover Planet 9 in that data.
Do you want to add anything?
We, as soon as you guys release that new one on the MPC, we'll fold it into our predictions of where things are. So I'm excited to see where it's really sitting, and that will inevitably move our search region just a little bit because there's so few objects that everyone changes it just a little bit. So I'm excited to see it. Where their search field is using the dark energy camera in Chile. So they're looking down in the southern hemisphere. We are concentrating on the northern extensions where we think it's most likely to be.
Elizabeth Bailey, did you want to add anything? No? No? Okay. All right. Let me see if there's any others online here. I think we got all of the online questions answered. Do you have any more questions here in the room?
Kelly B.
Yeah, Kelly again for Al Harris. Al, the astronomers care a lot about the absolute magnitude of these objects. NASA cares a lot about how those get converted into diameters for purposes of satisfying, targeting goals. Do you see a more pragmatic or longer-reaching value in what you've done outside of reducing the number of 1-kilometer objects, which is in itself kind of an arbitrary number?
Yeah, is this thing running?
Yep.
Yeah. Okay. I mentioned NASA's interest in diameters. Scientifically, we're very interested in the albedos of these objects, and so knowing diameters gives you albedos. The NEOWISE data set is terrifically valuable scientifically to help us pin down this albedo of the ones measured. That doesn't tell us about the real albedo object by object to the others, but it does have a huge science value. I didn't emphasize that, and you're right, scientifically we don't really care whether there's 800 or 900 out there, so on, unless one has their name on it. But down at the very small size, pinning down the distribution and matching that up with bolide data and so on, I think is, again, scientifically very interesting.
If I can follow up on that, there's at least 1 or 2 papers at this conference that call into question the systematic accuracy of the NEOWISE albedos that are being derived, and how might that influence what you're doing? And do you agree that there might be slop?
Well, the latest NEOWISE paper by Joe Massaro reports the 3rd year results, and I did talk with Joe for a while to see if they see any systematic difference between the post-cryogenic survey, which involves only the 2 short frequency 3 and 5 micron bands and is heavily corrupted by the reflected light versus the survey with the cryogenic survey when they're at 10 and 20 microns as well, and those have absolutely no reflected light, and so their modeling, I think, is much more secure there. Joe indicated that he hasn't seen any systematic shift so far. In other words, their modeling using just those 2 short frequency bands seems to be pretty darn good, you know. And the other paper that is right two away in the program is one by Nathan Mervold, in which he has called into question some of their modeling. I frankly see a convergence between those two people, even though they've argued back and forth, sometimes in a somewhat unfriendly way. But if you look at the abstracts of those 2 papers now, they're both quoting uncertainties in diameters from the NEOWISE data in the neighborhood of 15 to 20%. And in fact, the NEOWISE project, Joe Massaro quotes a rather larger number than Nathan, and that's just the reverse of what they were claiming earlier on. So hopefully that's going to converge and people can all be friends again, you know, because from my perspective, it looks pretty good. You know, the uncertainties are bigger than they have just been offhandedly saying 10%. Well, no, they're bigger. And so as a result of Nathan's investigation, they've bumped that up, but they've now actually bumped it up to more than his.
Any more online?
Yeah, you want to take one more in here first?
Yeah, first we'll take the one.
I'm Jack Drummond, Air Force Research Lab for Vishnu. How can you eliminate a man-made object for your asteroids, either spectrally or dynamically?
Sure. So I think dynamically, Paul Chodas has worked on this object to see if there is any, comparing like the pre-covery data from Sloan to current astrometry to see if there's any effects of solar radiation pressure. Initially, when he looked at it, there was none. And but I just talked to Dave Tholen in the hallway after my talk, and he said that he sees something. So that calls into question whether this an object is artificial or natural. The other thing is also that the anomalous spectral type makes this object, it's not a typical S-type, it's an L-type object. So we really need to finish building that instrument for LBT so we can go in the near infrared and actually confirm whether this is a real asteroid. Addition to that, I've been pestered by the Chinese space program people, so they're planning for a mission to this object. And so they want to really know whether this is a natural object or an artificial object. So they've been the primary one of the primary motivators for me to write that paper up. But at the same time, I think the follow-up work we want to do is to get spectra of artificial objects. I mean, it's a relatively large object. You have to have something in the order of 40 meters, and most of those are upper rocket stages. So it's a simple enough spectrum. It's going to be titanium paint, so we should be able to rule that out.
I can add a little bit to that, and in doing my population stuff, I've paid attention to some of these things that are potentially artificial, especially really in the small size. And this particular object has a relative velocity compared to the Earth of more than 10 kilometers a second, and it would be very hard to take an artificial rocket body and put it there, and if you did, you would really know, somebody would say it's theirs. It's not random space junk that just kind of, things that were used to go to moon missions and then the moon ejected it into the heliocentric orbit and that kind of game. It's definitely not one of those. So the orbit just makes it highly implausible that it would be an artificial object. In addition, it's rather too big.
We do have a few more questions online.
Okay, we'll take the online ones.
Okay, so these are coming again from Rick Lovett out in Oregon. This question is for Juliet Becker. He's asking if these 9 objects, including the new one you found, that go that far out from the sun are the only ones that do. In other words, is the entire population of these very far away TNOs apparently affected by Planet 9 if it exists? Or is this just a subpopulation of a larger group?
Yes, so there's a much larger group of objects. The subset that's being considered here is those that have average distances greater than 250 AU, which an AU is the distance between the sun and the Earth. There is a lot of objects with some major axis smaller than that, but they may go out at the furthest points in their orbit, they may pass past 250 AU. But it's thought that these objects past 250 will be influenced by Planet 9. The objects in the range of 150 to 250, not as much. And actually, I should mention that there's actually more than 9 objects that fit this class now, because in addition to the one found by Dark Energy Survey, there's also been a few more discovered by the OSIS team.
Okay, and then a follow-up related to this. You showed the plots with the red and green points, and he was wondering if any of the information drawn from that narrows the search window at all, or if, as Mike was saying earlier, you need to wait and see what the specific parameters of your new object are.
So the red and green plots of the Planet 9's orbit?
Well, he's not. I'm not sure if it was that one or the ones at the end where I think the ones where you showed all the parameters of the orbits of your new asteroid. But I'm not sure which it is actually.
It was an A versus E plot where you have the blobs of stability.
So if we can place better constraints on the
okay.
true... Okay,
Great.
thanks. If we can place better constraints on the true orbit of Planet 9, that does help know where it will pass in the sky.
Mm-hmm.
That computation of taking the orbit to the sky location is not something that I did in my work.
Okay.
Kelly, or first,
Jack.
Jack. Yeah.
Wait.
Excuse me, Jeff. What publication are you looking for?
This phase diagram here does not include inclination. How does inclination fit in this? I know Kuyo's was the highest, but are the rest of them also relatively high?
So that's a good question. So most of the other TNOs have inclinations 30 degrees, a little less than 30 degrees. And this is part of why these new objects from Dark Energy Survey will be so valuable, because the nominal inclination for Planet 9 is thought to be about 30 degrees. So finding objects with higher inclinations will help inform that orbit. And Dark Energy Survey is particularly well situated to find these new high inclination objects.
Kelly.
So if you wouldn't mind flipping back a couple to the first part of her presentation. I'm sorry, I guess it was an animation. You showed an animation showing how an object with a perihelion near Neptune's orbit would eventually get kicked out. Were you dealing with real objects there that exist now? And if so, what is the lifetime of those objects against ejection, just as is?
So good question. So these particular videos are of Kazoo. We also, so in the simulations, we used the true discovered TNOs and their measured orbits. The exact lifetime that the orbits will live depends on the exact parameters of the simulation. For these extremely unstable objects, they can live as little as 10 million years. Or for some of the objects, even less. For objects like Sedna, they are stable for the entire lifetime of the solar system.
Can I put in a little question here? Dynamics is one of my games from a long time ago. It seems to me that when you put the Planet 9 in there, you are going to induce eccentricity oscillations in the orbit, so these ones that are otherwise unstable, if the cycling is right, the Planet 9 would pull the perihelion out and thereby stabilize it. Is that what's going on?
So I would say more likely what's going on is the object is perturbed through interactions by Neptune and then is trapped in a location with a larger perihelion distance by Planet 9. Mm-hmm. So almost, yes.
Yeah.
I have a quick question for Al. So we've seen other papers that have come out recently about the population statistics at different sizes. Could you comment on more recent studies that have come up?
Well, I did show the one with Trekerico. If you can go to my presentation, I think I tucked a slide in at the end that...
It's like a backup slide.
Can you bring it up? Yeah, just cycle on to the end of it here. Okay. Ooh, don't go too far. Another paper that just came out, and by the way, is based on Dark Energy Telescope survey, is by Trilling et al., in which they claimed a population that, at first they said it agreed with Trilling, but in the final published paper by Trilling, it doesn't particularly. It's the one that's in the kind of lavenderish color with triangles. You can see on a log-log scale of 9 decades by 8 decades or something, it looks pretty close, but if you actually get out a ruler and measure that, the population as you go down to the smaller size range is considerably less. It's a full order of magnitude less than what Trilling and I get, and even more or less than what the bolide data would suggest. I'm also troubled if you really squint down on this, in the magnitude range of 20 and 21, the Trilling et al. Results actually declares a population that is less than the number in the red line given of already discovered objects. This brings to mind a famous expression by Max Planck, who commented, "Not even wrong." You can't have fewer objects. You can't predict fewer objects than you already know exist. You know, it's just simply not possible. And so I worry about this one. I think in general, in the large scheme of things, it's not bad. It looks pretty good. They were using a very small sample of data, but I think something has gone badly wrong right in that where that little notch in their data is that drops under the already discovered, and that could be the reason that they're underestimating as you go still smaller.
Thank you.
All right. I think we'll end the press conference here. Thank you to all the speakers. We'll have press releases related to the press conference. And I'll see you tomorrow at 12:15. We'll have 4 more interesting talks. Thank you for being here.